All right, so before we dive into trying to find a pivot and its distribution, let's start with a little bit of linear algebra review. So first, let me remind you what orthogonal matrices are. So we call a couple of vectors. So let's say everything we do will be in Rm. OK. So if I have a bunch of vectors v1 up to vk in Rm, then I call them orthogonal if they're inner products. Orthogonal if their inner products vi transpose vj is 0 for I not equal j. And I call them orthonormal if this is true and vi transpose vi, which is nothing but the Euclidean norm squared that I write with these double bars of vi is 1. OK, so and if I collect, we've seen this in another recitation video already. If I collect k orthonormal vectors into a matrix V, and then apply this V to a vector x in Rm, in Rk, and look at the squared norm of this, then this is x transpose V transpose Vx. And V transpose times V by these requirements is the identity matrix on K. So this is x transpose x. So it is the norm of x squared. In other words, if I hit a vector with a matrix consisting of orthonormal vectors then as columns, then this will give me the norm back. So this will preserve the norm. Moreover, if I manage to find m such vectors, then we call V orthogonal an orthogonal matrix. And that means, by exactly the same argument, that V transpose V is the identity matrix on M. And since these are square matrices, the same will hold true for VV transpose. So where do orthogonal matrices come into play? Most prominently in the spectral theorem. And I'm just going to give you a version on R for symmetric matrices. So what does the spectral theorem say? It says if I have a matrix in a square matrix in m by m, R to the m by m, that is symmetric, that means the transpose is the same as the matrix itself, then there exists an orthogonal matrix V and a diagonal matrix lambda. So diagonal means I only have entries on the diagonal, such that A can be written as V times lambda times V transpose. And this means nothing but the fact that A can be decomposed into orthogonal subspaces that correspond to eigenvalues and eigenvectors of A. What does that mean? I can rewrite this equivalently, multiplying from the right by V as AV equals lambda V times lambda. So AV is a collection of A applied to the columns of V. And v lambda is multiplying each column of v by lambda I. So this thing here is lambda 1 v1 lambda m vm. So in other words, AVI is equal to lambda I vi, and this is what we call an eigenvector. And lambda I is the associated eigenvalue of the matrix. And this is useful. So this is telling you that once you have a symmetric matrix, you can actually see it as a basis change on both inputs and outputs, and just a stretching operation that's going on, stretching or squeezing operation that's going on in that basis. OK. And I'll have to erase and continue with this, because now we're interested in a special class of symmetric matrices that's going to occur in finding the pivot.